My name is Sebastian Robic. I'm with Digital Europe, and I am here to present the Fudge 5G demonstration for private networks using service-based architecture. So the proposition of Fudge 5G is around unifying the service-based architecture, and the offering we bring with that is around service routing, telco-centric orchestration, and telemetry in a unified fashion for all enterprise services which we define such as 5G core or vertical applications. The demonstration here at this booth at EUCNC is within a private network setting, and we're utilizing SBA to increase the flexibility and to demonstrate the dynamicity which we can have in 5G core. So the proposition of Fudge 5G is essentially to slide in a platform layer between a service layer, which is basically for the enterprise services, 5G core and vertical application, and between the service layer and the infrastructure. Most importantly, these dotted lines between the layers are essentially representing programmable interfaces, allowing the north configuring the south. So from the service layer towards the platform, and from the platform layer towards the infrastructure. In the infrastructure, we assume that we have a unified access domain, which is based on Ethernet. So this includes the access network as well as within the infrastructure. So for the platform to operate, we would like to see Ethernet throughout. This is combined with an SDN-enabled switching fabric. So the routing layer of the platform integrates seamlessly with SDN. And we also would assume that the infrastructure offers some sort of programmable infrastructure for allowing our platform to be orchestrated in an automated fashion as either VMs or containers. Now, the platform, by sliding in this platform layer, we essentially enforce the functionality provided by the platform onto the services on top. The functionalities are essentially routing functionality, which in this case is a service routing component. We also have cloud-native orchestration for the layer on top. We add to the orchestration a telemetry component. So telemetry in that case is the is monitoring as well as the data analytics of enterprise services. And we also add slicing capabilities. But slicing here as a general concept of isolating resources, and if the isolation is done, to also enforce the QoS requirements. And then on top, the service layer is essentially, as I said before, a 5G core vertical application, and as there are only packets being pushed through the platform, we assume that the services on top are ideally microservices that are implemented in a stateless fashion, allowing the platform here not only to route packets in a service routing fashion, but also the lifecycle management of the services on top. So the current 5G system is essentially the combination of a service-based architecture for a 5G core and combined with let's say legacy interfaces originating from a before SBA world. So what we can see here in the system architecture of a 5G core is the SCP, the Service Application Proxy, which is an optional component at the moment, according to release 17 or even 18. And with this SCP in the orange line, which represents the service-based interfaces, we have network functions that actually still live in two worlds, such as the AMF, which lives in the SBA world with the NAMF interface, as well as in the legacy world with peer-to-peer connections towards the access network, in this case N2. The same applies to the SMF, which has through the NSMF interface, lives in the service-based architecture world, with the N4 towards the UPF in the legacy peer-to-peer world. And the UPF as the user plane function, as a 5G core network function, is not service-based at all. So it does not have a service-based interface, and it's not considered to be realized as a microservice. So what we do in Fudge, is, besides demonstrating various technologies around TSN, 5G LAN, we also have architectural changes for a, let's say, more beyond 5G system. So what the proposition is here to unify but still be SBA and Release 18H compliant is that we slide in the SCP as a routing functionality very similar to the concepts of the internet, meaning the SCP is not addressable anymore, such as on the internet, where if a service that resides on the internet, somewhere in the cloud, for example, is addressed in a browser, we do not address the internet, we address the service. And the same what we do in fudge, that network functions address each other directly, and the SCP offers transparent service routing to all the network functions on top. Also, as the evolved step towards a beyond 5G system, we allow the N2 and N4 traffic, so the G-Node B and the UPF traffic, to be routed through our SCP, given that the SCP also is not only service routing for HTTP traffic, but it actually understands and supports any IP-based communication. So we allow on the N2 interface the STP connections towards the AMF to be routed over the SCP into the AMF, as well as on N4, PFCP or OpenFlow to be routed between UPF and SMF. So on this slide now here, we see the testbed that is located in London, which serves also in fudge 5G as the experimental testbed for integrating our technologies before it goes out into the trial locations in Grenoble. So what we see on the slide is essentially a infrastructure, including the platform. The infrastructure is composed of OpenStack compute hosts as well as bare metal deployment of the platform. The dotted lines here represent the OpenStack compute hosts. So we have a 3-tier compute infrastructure basically with a data center on top, so 2 data center compute hosts. We have 3 edge deployments interconnected through an SDN switching fabric. And at the bottom we have essentially the on-premise deployment of the far edge, which includes the UE, the G-Node B, and compute hosts for platform components. Now, as part of the platform are what we call service hosts. They are either in OpenStack virtual machines, or locally here at the bottom, the FE1 and Sage, for example, is actually Linux container. And into those instances, we actually orchestrate enterprise services, in this case a 5G core. So what the actual deployment looks like is to demonstrate the private network setting where a 5G core partially resides in the cloud and partially on-premise. We essentially deploy AMF, UDM, NRF, SMF, and AUSF in the cloud in the data center, and we deploy the UPF locally on-premise, including the vertical application, and then from the UE, the actual application. Now, the application we're using here to demonstrate traffic being routed locally is a health monitoring application that uses synthetic data to push towards a vertical application that has a web interface, which I show you in a moment. So the actual SBA demonstration, which we have here at the EUCNC booth, entails the deployment of a 5G core, the attachment of a 5G UE to this core, and then the remote application started as part of the procedure when starting the UE. So what I'm doing first is I will now deploy a 5G core, and while it's deploying, I will walk you through the dashboard we have to visualize what is going on in the platform. So what we here have on this dashboard is essentially the telemetry component of the SBA platform. You already see that a couple of graphs here already have data, the others still are in the no results mode. This is because while explaining the topology, we kicked off the deployment of a 5G core. You can see here on the right those 2 numbers, where the numbers represent the containers that are deployed in a particular location. So here, that is the data center location. So we have 6 containers deployed representing the network functions I had in the previous slide that reside in the cloud. And on premise, we have 1 network function deployed, which is the UPF. So we see here on top the CPU utilization as well as the bits per second for each network function. And we have from AMF, also AOSF, SMF, UDM, and NRF. The initial peak we can see in the NRF in traffic, as well as then the CPU for all network function is essentially the initial step of coming up and the registration with the NRF for all network functions. So the core now is basically ready. What I have to do next is I have to restart basically the GNode B, because we do register the GNode B against the AMF using an FQDN. In this case, it's called AMF.focus, because that is a 5G core from Fraunhofer Focus. And our SCP basically routes the traffic towards the AMF instance. Every time we redeploy, we also get a new IP address for the AMF. And that is why I have to restart now GNode B by hand, because the GNode B we are using here in this demonstration only does DNS at the beginning of a boot up. So once the GNode B comes up, it resolves. It now has attached already to the AMF. We see a bit of traffic also coming into the AMF here, meaning the GNode B has registered. And now we are able to allow a modem to attach. On the top left here on my screen, we have a web interface into the 5G modem, or into the UE. If I press attach, we are sending AT commands to tell the modem to attach to the base station. The SIM card is pre-provisioned. The details of the SIM, allowing the core to authenticate and to register UE, has been also populated at packaging time of the core, so before we deploy the core into the UDM. So if I attach the UE, we will see momentarily the messages for the registration of the NAS protocol into a GNode B. And we already see that the UE is now attached. And we see on the top right that the health monitoring application receives data from the UE now that has been deployed as containers. And if I detach the UE, obviously the data stops flowing in, and we will also see then in the slide in the dashboard here that the UPF will have seen some traffic that has been carried from the UE locally through the UPF into the data network. And this concludes our presentation here. Thank you for watching.